All right. First example is a pretty straightforward example. I just want to make sure that we are all familiar with the concepts and how things work for a simple case, and then we'll move to something that needs a little bit of more uh, calculations and probably digging deeper into the knowledge we have uh, from before. So this one, we have a disk. It's rotating about point O, right? So it's a rotational motion. Point O is fixed. We know the mass moment of inertia, or as it's referred to it here, moment of inertia, 20 kilogram meter squared. Based on the unit, we know it's the mass moment of inertia. At t equals to 0, the disk is stationary, so the motion starts from 0, right? The velocity, initial angular velocity is 0, and the disk is subjected to a constant 50 Newton meter torque, right? Counterclockwise direction. Now, what did they ask? They asked us to find the magnitude of the resulting angular acceleration of the disk. So we're looking for alpha, which is caused by this force, this torque applied to the disk. And then we're asked to find how fast the disk is rotating at after 4 seconds. And specifically, they told us to find the rotation in RPM. RPM, I'm not sure how familiar you guys are if you've seen it before. RPM is a revolution per minute, or revolute per minute. The revolution per minute is number of times, let's say, this disk rotates in a minute. It's just a different unit for rotational motion. We have radian per second. We can also have revolution per minute. This is more common when you're in industry dealing with rotating machineries. So it's a must. You have to be familiar with that. Now let's just first take a look at part A. So part A, let's see what can we do about that. Well, obviously we're dealing with the dynamics of an object. We're going to start with free body diagram. Right? So let me draw a free body diagram first. If I can find some, let's use this. Why not? Okay, so this, let's consider this as our disk, and I'm going to take this as the point that the disk is rotating about it. This is point O. We have two forces applied to that point. Well, that's where the, I don't know what happened to the rest of the O. There you go. These are the forces from the floor or the ground where the disk is pinned. So this, let's say, is OY, force in X direction, OX. So I have two forces there. I have the torque applied to this, and it's 50 Newton meter. And I also have the mass of the disk, which is M, the weight, the effective weight, which is mg, downward. Now this is equal to, let me write it here. This is the free body diagram we have. Now looking at kinetic diagram, let me bring same here. Looking at the kinetic diagram, we'll get pretty much only one thing. We'll have rotational motion, so there's not that much there. If it's point O here, the only type of acceleration we have is the angular acceleration. There is no other component for acceleration. So only thing we have is kinetic diagram would be I-O alpha, the kinetic components. That's what we do, right? Forces and then kinetic diagram, and then we make them equal. This is kinetic diagram. Okay, so the equation, the Newton's second law, it's a rotational version, will tell us all the moments around point O is equal to I-O alpha. I'm going to take the direction of the motion as positive. So counterclockwise, positive. You do that. Well, from this, from the free body diagram, if you take moments, find the moments about point O, OX, and OY, and weight are gone because all of them are passing through point O. So there is no moment caused by these forces. The only thing left is the torque applied, which I put it directly here because it's a moment. 50 is equal to, on the right side, IO alpha. And I know what IO is. I is given, I about point O is given 20, so I can easily find the angular acceleration. I can find alpha as 20, left side, which is 50 divided by 20. And that will give me 2.5 radian per second squared as my angular acceleration. This is the answer to part A. I was asked to find the angular acceleration. Now, to find the answer to part B, and how fast is this rotating? Well, for now, just forget about RPM. Let's find out how fast the disk is rotating. So for angular velocity, what did we have from kinematics? We had alpha angular acceleration is equal to the time derivative of angular velocity. I write it. Hopefully you remember this from kinematics. Just move things around. Take integral, goes from T1 to T2, goes from T1 to T2. There I get, well, the motion starts from 0, stationary, ends at 4 seconds. Alpha dt is equal to, it goes from 0 to the angular velocity that I'm looking for. I'm going to call it omega 2. Well, I have to fix the limits for this one. This should be omega, right? The integral is, we're taking integral over omega. So it goes from omega 1 to omega 2. Omega n is 0. Omega 2 is just omega 2. That's what I'm looking for, d omega. Now, alpha is constant, right? So it comes out. So we'll get, from there, I'll get omega 2 is equal to 4 alpha. 4, and that would be 4 times, I found alpha was a constant, 2.5. That gives me 10 radian per second. That would be the velocity of the disk after 4 seconds. Now, this velocity is in radian per second. I have to convert that into revolution per minute, right? RPM. How do I do that? Well, I'll say omega 2 is equal to 10 radian per second. Oops, this should be second. I don't know where to put 10. Radian per second. Right? I multiply that. Well, I'm gonna go with radian first. I want to get rid of radian. So I know 1 revolution. How much is 1 revolution? 1 revolution is 2 pi. Right? So 1 revolution is 2 pi. Put it this way: 1 revolution is 2 pi. And then again, now I want to get rid of second because I want it to be revolution per minute. So I'm going to convert the second. So each, 60 seconds is 1 minute. Do this math, you will get 95.493 revolution per minute, or as they call it also RPM, revolution per minute. So that would be the answer for part B. That's the angular acceleration, angular velocity of the disk after 4 seconds in revolution per minute.